Hello, I'm Hafner, and I want to talk to you about our work on the design space of plane elastic curves. The method that I want to talk about is an alternative to steam bending, known as active bending. The promise of this method is to save costs both in fabrication and transportation by using flat beams directly for construction without any kind of pre-bending. And what we can do to control the geometry of the curved shape is to adapt the stiffness profile of every element. So let me give you an idea of how we can control the stiffness profile. One way is to taper the width of the beam, because having wider and narrower sections selectively changes the stiffness, which has an influence on the final shape. One of the reasons why active bending is not as frequently used as steam bending is that there are several challenges related to the design of active bending structures. First of all, it's not immediately clear how large the design space even is, so which kinds of shapes can be achieved using active bending? And now the main result that we prove in the paper is the following theorem. For a given curve gamma, we can satisfy the moment equilibrium equation with appropriate choices for k, a, and b, if and only if there exists a line that intersects gamma exactly in its inflection points. So let's try and put this theorem to use by deciding for a few example curves which ones can be achieved by active bending. This tells us that the curves at the top can be achieved as equilibrium curves in active bending, but for the curves at the bottom, this is physically impossible. And the next natural question is, how can we physically realize a design like this? In other words, how do we determine the stiffness profile that realizes a given curve? And it turns out that a very small linear program with only 4 variables suffices. We can use the linear program to design simple structures in active bending, such as this one. This model is about 1 meter long and is composed of 31 arcs. Each flat element is cut from cardboard and then curved by inserting it into a 3D printed base that has indentations to enforce the boundary conditions. Not every design which can be realized in theory is very practical for fabrication. So this leads to the question, how can we improve such designs? If we take one of these section curves and compute the stiffness profile with the linear program, we will see that it has this extremely narrow section that makes it unusable in practice. But we can run our algorithm and track how it decreases the objective value and how it modifies the target curve and the stiffness profile in the process. So the objective value drops quite rapidly, and if we look at the stiffness profile, we can see that the narrow section disappears as the algorithm progresses. The target curve is modified in the process, but the overall deformed shape is preserved. And after we optimize the other plane section curves on the surface, this is the result that we end up with. We applied the same algorithm to make several physical models, for example this one of a horse, which was based on an existing 3D mesh. This model shows an architectural shell, which we have approximated with perforated elastic strips to achieve a stylized look. And finally, this is our largest physical model, a ceiling lamp with a diameter of about 1 meter. The base material is plywood, and at this scale it would have been very expensive to make molds for every single strip or to 3D print the entire model. Let's also compare physical models of the stabilized and initial curves. The stabilized solution on the left is very robust to physical perturbation and always snaps back into the target shape. Meanwhile, the initial curve is unstable and always snaps either up or down into a different equilibrium state, and it cannot keep its shape in the target state. And with this, I'd like to thank you very much for your attention.